This is UCF Senior Design Group 12 with the polyphonic analog to MIDI converter device. In this presentation, we're going to talk about everything that went into the design, development, and testing of our senior design project, including our motivation, objectives, the requirements that we set for ourselves, and all of the steps through our design of the hardware and software, and our development process, including the budget, the integration steps, the challenges and pitfalls we faced, and how we eventually ended up testing the device. Our main motivations for choosing this project were so that we could apply our knowledge of electrical design to musical technology, because all three of us have background in and a passion for music. We wanted to create a novel device with applications for performance and studio settings using MIDI, which stands for Music Instrument Digital Interface. It's a digital standard that's widely used throughout the music industry. No device on the market currently claims to perform real-time conversion of instrument signal to MIDI for multiple notes at once. This is called polyphony. There are, however, devices that do analog to MIDI conversions for a single note at a time. That's monophonic conversion. What we wanted to accomplish here was to use the fast Fourier transform and frequency analysis algorithms to identify multiple musical pitches at once. We'd be able to accept input from quarter-inch cable, which is standard for electric instruments like guitars, basses, and most synthesizers. And we want to be able to interface with a MIDI instrument or a digital audio workstation, DAW for short, as a MIDI controller. And finally, we want it to be compact and portable enough for use in live settings. This way, this is sort of a dual-purpose device where you can use it for sheet music transcription or MIDI controlling in the studio setting, or you can use it as a supplement to whatever you're doing in a live performance. Our requirement specifications, here are some of the most important ones. First, for polyphony, this is the number of voices that are observed at once. We're basing our design around the electric guitar, and the electric guitar has 6 strings, which means it can sound 6 notes at once. So that's the amount of polyphony that we're going for, 6 voices. The MIDI stream latency, this is our target time between the reception of the signal and the note output of the device. We're shooting for 100 milliseconds, which is a pretty significant delay, but we figured that if we could get down to 100 milliseconds, then with certain improvements to the hardware specifications, certain improvements to the software optimization, we could get it down to a much more suitable, usable range. The note accuracy is a ratio of the number of correct notes detected and the total number of notes detected. And we're shooting for 80% accuracy on our note detection. The minimum note pitch, the lowest frequency that the device can detect, we're shooting for 82.41 hertz. This frequency is the frequency of the low E string, note E2, on the electric guitar. Here we're going to talk about our design. In front of me now is the hardware block diagram. You can see, kind of flowchart style, that the analog signal goes in through a quarter-inch input, and it actually can pass through the device to a quarter-inch output. This is a feature of our preamp that we'll get into later. That same input signal is split and goes into the preamp, where it's filtered, bandpassed, and then it's sent to the analog to digital converter in the processor. From the ADC, it's going to have fast Fourier transform applied to it to put it in the frequency domain, and then note translation is going to be done. That's sent out to the MIDI controller bus, which will send the digital MIDI signal to the MIDI compatible device that we're interfacing with.
So this is our block diagram for the software. This is our initial version, which we've had to make certain changes and revisions as we actually put it together and tested it. So initially, the input comes in from the ADC and it's converted to usable data via a driver. And this data is stored in a sample buffer, which will then be used to turn into a frequency array via a fast Fourier transform algorithm. In this case, we found that we weren't actually able to use signal padding to increase the resolution in the frequency domain, as it would increase the time of the fast Fourier transform significantly, since the algorithm is not linear. Um, and from there, that outputs frequency spectrums, which we're able to use in the next section. So from there, another omission we had is we omitted the magnitude-based noise filtering, where the initial idea was to cut out any very low magnitudes that couldn't be notes or harmonics in the first place. That would just be noise, but we found that we are getting some harmonics that were very, very low magnitude and some noise that were louder than those harmonics. So we found that we did need to use those harmonics and we couldn't cut them out. Um, and from there, we ended up, rather than using Q factor-based filtering, we decided to go with a harmonic product spectrum algorithm, which decomposes the harmonics and multiplies them into the fundamental bends, which will exaggerate the magnitudes of the fundamental notes being played. And this allows us to choose the fundamental frequencies and distinguish them from the harmonics and any sort of noise. So from there, we detect the notes via a scaling threshold that scales based on the RMS of the input signal, because we found that the thresholds were not static as the note sustained and the volume of the note you played changes. And we kept a 6-note output array, which at all times holds up to 6 notes, which is used by our MIDI output driver. Our MIDI output driver keeps an eye on what notes are in that array, and if a note is added or taken away at any point in time, it'll send the note played or note off signal via the MIDI protocol through our MIDI output. These are parts of the schematic for our analog preamp. The main purpose of the preamp is to take the input signal and scale the magnitude to a usable amount based on the input, as different instruments will oftentimes have very different output magnitudes voltage-wise. They won't be a consistent line level. And then, as a lot of instruments are passive, and so the different passive pickups in those instruments will output very different magnitudes. So some of the features include a buffered pass-through, which allows you to use your unaltered signal at the same time as the device to play through an amplifier or any other uses you may want for your analog signal. And the voltage, the amplification of the voltage on the signal is variable with a potentiometer to adjust for different instruments, as I mentioned before. And then another feature is that we use a several stage active bandpass filter to cut out any high frequencies to reduce any sort of aliasing issues that may happen on the software side. And then we also cut off some low frequencies that may be caused by resonance in the guitar or any other instruments that could cause issues with the note detection. This is just the buffered pass-through schematic, which you can see it just has a zero gain op amp with a DC coupling capacitor to ensure that it is centered on ground on the output. And this is the voltage amplification section. You can see the toggle switch switches between settings on the gain, which is set by the resistors in the feedback loop of the non-inverting amplifier. And so between the potentiometer and the switch, there's quite a lot of options for how much gain you can receive from the amplifier. And here is our multi-stage bandpass filter. It cuts out frequencies at about 20-ish hertz, as the cutoff point is at 20-ish hertz, but it still lowers the frequencies above that a bit, and we don't want to affect frequencies like 80 hertz too much, so we lowered the cutoff lower than 80 hertz. And then it cuts off high frequencies at about 12,000 hertz, the current version.
This device requires two different voltage levels, two different power rails, 5-volt power for the op amps in the preamp section and the MIDI output circuit logic, and 3.3 volts power for the MSP 430. The DC to DC converters that we were using for this include a 9-volt to 5-volt DC to DC converter using the TI Webbench tool. It was designed with around the TPS 563231 chip. The 5 volts to 3.3 volts DC to DC converter was supposed to take the output of the 9 to 5 converter and step it down further for use by the MCU. Everybody in the group contributed different parts of the schematic from either Autodesk Eagle or LT Spice schematics, and all of these schematics were brought together and stitched together in Eagle. The PCB design was also done in Eagle. We used a 2-layer board so that we could get a large ground plane on the bottom layer for good consistent grounding across the device. We ordered this from 4PCB, an American manufacturer, and it was assembled with assistance from Quality Manufacturing Services and S-Tronics Test Systems, 2 different engineering companies here in Orlando.
The microcontroller that we are using for the core of our digital logic is the TI MSP 430 FR5992. The CPU clock speed can go up to 16 megahertz, and it uses a familiar architecture and development environment that we have used in the past in some of our other classes. And that is why we selected this microcontroller instead of other alternatives. This microcontroller includes hardware acceleration for the fast Fourier transform and the digital signal processing operations. It is low power and low cost, and it features the peripherals that we need, such as a 12-bit analog to digital converter with up to 200 kilohertz sample rate, a UART and SPI serial interface, and 8 kilobytes of RAM. To control the ADC, we use a ADC driver that makes the ADC collect samples at a rate of 12.8 kilohertz. This makes the Nyquist frequency 6.4 kilohertz, which is close to the note G8. We could choose to have a sampling frequency that allows us to detect notes up to G9, which is the maximum note defined by General MIDI 1. But this note is barely audible by people, and very rarely can any analog instrument play this note. The sample resolution that we use for the ADC is 12 bits. Normally we would only need 8 bits of resolution because the MIDI note velocity is only 7 bits. But the operations that are done on these samples, such as determining the magnitudes of the frequency spectrum, those operations will reduce the resolution. The ADC input is double buffered, meaning that every time every time a sample buffer is filled, it is swapped with another one to prepare to read more samples from the ADC. And this allows the microcontroller to receive analog inputs while performing the FFT. To generate a spectrum of frequencies that that describe the samples that are being read by the ADC, originally we considered doing a 2048 point fast Fourier transform with a 12.8 kilohertz sample rate. And this would capture the frequencies corresponding to notes E2 to G8. However, this was not feasible because it would require a buffer latency of 160 milliseconds and at least 4 kilobytes of RAM for the FFT. And the problem with those numbers, first, for the buffer latency, this is how long it takes for one sample buffer to be completely filled. And in order to do the 2048 point fast Fourier transform, we need 2048 points, and it takes 160 milliseconds to collect that many points. And in terms of RAM, the hardware acceleration that allows us to do the FFT in a fast way can only use up to 4 kilobytes of RAM, and so this FFT would not be possible because especially when we use two buffers instead of one, and at the same time doing this 2048 point fast Fourier transform, we end up with needlessly high density at the highest frequencies of the spectrum, which is unnecessary because the note scale is logarithmic, whereas the frequency spectrum is not. Instead, what we chose to do is to split the fast Fourier transform into 3 stages across different pitch ranges. For the third stage, we do a 512 point fast Fourier transform, which only requires around 40 milliseconds worth of samples, and this allows us to capture the notes from E4 to G8. Next, we do the second stage. We do a 64 point fast Fourier transform with the same data that we used in the previous transform. This allows us to detect frequencies corresponding to notes E3 to G4, and this FFT is done each time the previous one is done. And what that implies is that the FFT is that the buffer for the second stage is only half filled when the FFT is done, and the same applies to the first stage, which takes the sample input from the second stage and does the FFT on that, and that allows us to detect the notes E2 to G3. And likewise, the FFT is done when the sample buffer for this stage is only a quarter filled. In order to pass samples through the lower stages, they need to be passed through a low pass filter, and the amount of samples that are passed is determined by the fraction of the higher rate sampling rate compared to that of the lower stage. So currently we use an elliptical infinite impulse response filter. And what this does is it reduces the effects of aliasing because of downsampling, because that is essentially what we're doing when we pass these samples at a lower rate to the lower stages. The overall buffer period is reduced to around 40 milliseconds using these methods, but this comes at a cost of lower accuracy at the low frequencies. But using the note detection algorithm, the accuracy at high frequencies can make up for this.
So our initial design for the note detection algorithm first had the magnitude-based filter, which I mentioned earlier in our presentation, which we decided to ditch as a result of the harmonics being very low magnitude sometimes. And then we decided to get rid of the Q factor based filter as we didn't have a high enough resolution from our FFT to be able to reliably determine any sort of Q factor on the peaks from the FFT. But instead we relied almost entirely on the harmonic product spectrum, which we did have to do certain things to make work reliably. So we found that the harmonic content as notes went up tended to have a different response. So we changed the harmonic response for different ranges of frequency bends to further emphasize higher harmonics, and as a result, it'll give an even magnitude across our detection spectrum. And then we have the final threshold, which does scale based on RMS, as I mentioned earlier with the block diagram. And most importantly, this entire algorithm was designed to avoid needless divisions or right shifts and completely avoid any floating point operations. So and even if it did, it would still be in linear time, but since our microcontroller doesn't work well with those operations, we used a lot of left and right shifts and made the note detection very, very optimized to reduce latency. You can see here the harmonic product spectrum and how it works, and you can see how the spectrums are divided into different integer multiples, and that results in the harmonics being multiplied into the relative fundamental frequency bends to emphasize them.
So, in terms of the MIDI stream, there are only three kinds of messages that we need to worry about: the note on, the note off, and the pitch bend messages. Currently, we only use the note on message since it serves a dual function as to enable the playing of a note and to stop the playing of a note. The stream consists of status and data bytes, but we can leave out the status byte for each message if each subsequent message is the same type. And what that means is that we only need to send the status byte once at the beginning of the stream, since all we are sending are note on messages. The basic MIDI output physical layer implementation uses a universal asynchronous receiver transmitter, a NOT gate, and a transistor. And the required baud rate is 31.25 kilohertz. However, our implementation feeds the UART output back into the microcontroller, which outputs the inverted signal using a digital output pin.
For our expected budget, which you can see in the table on the right, we have it broken down by item with a total of $450 that we expected to spend. We ended up spending $420, so we were very close to our estimate, and we're happy to come in under budget rather than over budget. $240 were spent on the PCB, and $180 were spent on parts. There are other costs that weren't factored into the budget, like buying a new soldering iron, instrument cables, and other expenses. But those are items that we get to keep afterwards, so we're not counting those.
So for the initial integration and physical prototyping, we first started with the most simple circuit. In this case was the analog preamp. We were able to breadboard with simple passives and a few op amps. So we were able to verify the gain and the frequency response before we ever put the actual PCB together. And then we used this preamp in conjunction with our dev board to test the initial early versions of the note detection algorithm.
Right, and with the dev board and the preamp prototype, it gives us a very close approximation into the functionality of the final circuitry. And so using these two systems combined, we are able to develop the source code and have it work as if it were live on the board.
With the PCB assembly, the blank PCB was designed to accommodate 8 different hardware blocks, 5 of which ended up being cut due to component failures and time constraints. This includes our power sources that were on board, which shorted out and were destroyed, and some features that got cut, like XLR ins and outs and USB compatibility. Wire pads were used to attach test points and external pads, such as I/O ports, switches, and potentiometers. The assembled PCB features hardware for the preamp, the MCU, and the MIDI output circuit. Just the core parts that we needed for basic functionality.
Some challenges and pitfalls we had included a lot with the note detection. So we found that oftentimes the thresholds were very, very, very sensitive based on the input response, which could vary greatly based on how you're playing your instrument, what instrument you're playing, and all of that. So we had to find a way to have a scaling threshold that approximates what the threshold should be based on the input RMS value. And this gives us a good approximation that allows the note detection to work with several instruments and several different volume levels. We also worked on clamping the input signal, and we found some issues with that, and we decided to let the scaling thresholds deal with varying magnitudes rather than clamping.
We also found a few problems originally with the MIDI transmission, where the baud rate wasn't being generated cleanly, and that would cause the output to not be aligned to the actual baud rate required. And to fix that, we ended up using a different clock source whose frequency was a multiple of the baud rate.
Some of the issues that we ran into with the PCB were a lack of test points and no ability to isolate hardware blocks for testing on the PCB. Both of these things are contributing factors to the component failure that we experienced, wherein the 9-volt to 5-volt converter circuit caused a 9-volt to ground short. This destroyed the MSP430 chip that was on that board. Thankfully, we had a spare. And the entire power system failed as we watched the 5-volt to 3V3 converter and the 5-volt to 48-volt converters go up in smoke. Finally, we'll get to the cut features. The complexity of the core functionality was what mainly drove us to cut these features. It took a long time for us to get the note detection algorithm and the MIDI output working the way we wanted them to, as well as getting the preamp tuned exactly where it needed to be for the guitar. The 48-volt phantom power was one of the victims of the power system failure, and we ended up not implementing that again, partly because we also decided to cut the XLR input and output. Without the XLR input and output, there's no need for 48 volts phantom power, as that's used to power microphones. USB connectivity was also cut, because it was simpler and more efficient, and also more widely applicable to use MIDI output instead of USB output. If we can only have one, MIDI output is the way to go. During testing, we found that 83% accuracy was held up for single notes, which is above our 80% threshold. But there were some problems with chords where we had 51% accuracy. This is still more polyphonic accuracy than all of the other products on the market. And if we work on it, we can get those numbers up. The MIDI stream generation latency came out to be only 56 milliseconds, which is well under the 100 millisecond delay that we had allotted for ourselves. That's it.